In this video I'm going to talk about least squares estimation. Least squares try to fit a model to the data, and there is no assumption about the distribution and statistics of data. Actually, it's a numerical method. Let's get started to see how it works. We have some data. For example, this is our data. Here are my data and my observations. For example, I have n samples, and I'm gonna fit a model to this data. I try to model this data with a constant model. For example, this is my model and consider it as signal model. It's a constant, for example, equals to a. Of course, I will have some model error. For example, this distance between observations and model is model error, and I'm gonna find the best model to have the minimum error. Error is observation minus signal. We consider this as error. And then I try to minimize energy of errors. Try to find A to minimize the my cost function. Actually, it's the sum of squares error. I just need to take derivative. Set to 0, and I have minus 2 equals to 0. And finally, the estimate will be sample mean. And this is the LS estimator for this problem. Let's consider more general cases. I have an observation vector and signal model. I consider it as h theta. That means it's linear combination of these vectors. I call them signal vectors. The signal or the model is the linear combination of signal vectors. Signal vectors are known, and I am gonna find theta, the best linear combination of these signal vectors. Error is observation minus signal, and the cost function or the least squares criterion try to minimize energy of the error. I can write it like norm of error power of 2. And we can write norm as E transpose E. So I can write and I'm gonna find theta which minimize J. For this you only need to take derivative with respect to theta. It will be minus 2 H transpose X minus H theta must be equal to 0. I call this orthogonality principle. This is the error and this is the signal vectors. An error must be orthogonal to the signal vectors. Orthogonality principle. Let's compute this. H transpose X equals to H transpose H theta. Finally, I will have theta hat equals to H transpose H inverse H transpose X. Let's interpret this. I wanted to close X to H theta. Actually, I wanted to solve this linear equation. But H is not a square matrix, so I multiply both sides of this equality to H transpose to make it a square. And now H transpose H is a square matrix and I can take inverse. So I will have H transpose H inverse H transpose X. This is the least square solution of norm X minus H theta equal power of 2. The signal estimate is H theta hat equals to H transpose H inverse H transpose X. I just substitute theta hat with its estimate. And I call this term projection matrix P X, which means we project observation vector to the signal vector or to the space spanned by the signal vector. P is projection matrix. This projection matrix has two properties. First, it is an idempotent matrix. What does it mean? It means P power of 2 equals to P. We can deduce P power of K equals to P. Why this is true for projection matrix? Because when we project a vector to a space, if we project it again, it doesn't change anything. It means if we project x to the, for example, signal space, if I project this vector again to signal space, nothing will change. That means P2x equals to Px. You can multiply this by itself and you will see nothing changes. Another property is projection matrix is symmetric matrix. P is a symmetric matrix. Idempotent matrix is a singular matrix and its eigenvalues are 0 and 1. Let's verify this. Px equals to lambda x. If I multiply both sides by p, I will have p2x equals to lambda px, which is lambda 2x. That means px also equals to lambda x equals to lambda x, and lambda 2 minus lambda multiplied by x is 0. Finally, lambda minus lambda is 0, and the eigenvalue is 0 and 1. When we have 0 eigenvalue, that matrix is singular. Why it is singular? Because there are we can find many vectors that they have the same projection. And for example, in two-dimensional, consider this vector, and many vectors. If I project them to the x space, I will have this projection vector. So projection matrix must be singular, because if it is non-singular, then that means we can find a unique vector from the projected vector, which is not possible. If I consider J and put theta hat on it, we have x minus h transpose x we will have another projection matrix, which is I minus h transpose transpose, which is I minus p. This matrix is orthogonal to the projection matrix P, and I call it noise subspace. That means, look at error vector. Error is x minus s hat equals to x minus px. It's I minus p multiplied by x. It is that means it is the projection of observation vector to the noise space. Let's recap our discussion to a sentence. We have an observation vector. We project this vector to the signal subspace by P. Px is the estimate of signal vector. And there will be error, which is the projection of observation vector to the noise subspace by using this matrix. Hopefully you enjoyed this video.